Hi, and thanks for everybody for joining. It was an honor to join this typology series on design for additive manufacturing centered around the NFL Football Helmet Design Challenge. And in case you're watching this in April 2020 here, as it's being given live, hopefully you can divert your attention from the COVID-19 concerns as we explore how additive manufacturing can be used in other areas of the medical world, namely concussion prevention and sports protection. So my goal for the next 30 minutes is to quickly, and I mean quickly, provide you with some frameworks to help make additive a viable solution. Ultimately, how to make AM, quote, feasible, unquote, for production applications. And I'll explain in a second why I wish I would have made the word feasible on this slide like 100 times bold. But first, here's me. My name is David Busacker, and I'm a technology consultant with a developed expertise in additive manufacturing. I first got involved in additive in the University of Minnesota, first taking, then teaching an introductory course to AM technology. From there, I joined Stratasys, the world's largest 3D printing company by a handful of metrics, as an applications engineer. And that is where I got to know Stratasys' biggest competitor very well, the status quo. I realized that the entire additive industry needs faster adoption, and that's why I made the move to Blueprint, a technology consultancy that Stratasys acquired in 2014. The mission of Blueprint is to help our customers make sense of how additive, a very big solution, fits into their business, an individual custom problem, in a way that makes sense. Okay, but enough about me, enough about Blueprint. Let's talk about you, specifically how I can help you stay awake during this webinar. I don't know about you, but sometimes I use webinars to help fall asleep at night. And nothing makes me drowsier than a webinar that I'm watching that I know is not intended for me. Well, this webinar is intended for you, so wake up, because the problem of scalability in additive manufacturing is one that affects almost every dimension of anything related to additive manufacturing. You don't have to be a contestant in the NFL Football Helmet Challenge or even nearly as excited about football as these two Vikings are. You may just be interested in pushing the boundaries of AM design, the way that Entopology is doing with their architected materials and generative design. Or if you're not doing either of those design-heavy things, perhaps you're looking to deploy AM in a production application or in some sort of other way. Regardless of what your stake is in additive, one of these things probably applies to you, and I have you in mind with the message of this presentation. If none of these is interesting, okay, well, you can go ahead and doze off then. So I've only got 30 minutes, probably 25 at this point. So we've got lots to get to. My goal, again, is to show you where additive manufacturing gets held up in its feasibility for scalable production applications. So first, I'm going to describe to you how the sphere of additive manufacturing capability has grown so that we're even thinking about putting it between two enormous football players that are running at each other full speed. Then I'll describe to you the three biggest problems with the additive manufacturing scalability: value, data, and change. I'll show you why they can be a problem, and then also how to go about circumventing the problem. But first, as I mentioned, there is a special relevance to the topic of feasibility to anyone hoping to win the NFL Helmet Challenge. To keep the rest of you guys awake, remember that's my second goal, let's all get up to speed on this challenge. No pun intended. The NFL Helmet Challenge is a $3 million innovation challenge held by the NFL. It's part of their Play Safe, Play Smart initiative for making the game of football safer. So what's the challenge? Groups of researchers, manufacturers, and companies all over the country are working to design a better helmet, one that's better than anything else on the market today. The competition began last year, and teams are already hard at work with the final submission date of next summer, July 21st, 2021. And without a doubt, additive manufacturing will play a role in the success of the winning submission. Why? Why are we even thinking about putting a technology that was called rapid prototyping until only 10 or so years ago? The truth is that additive manufacturing has come a very long way in the last 5 years. The design freedom that once made additive manufacturing so attractive for beautiful, if fragile, boardroom prototypes has begun transforming the world of manufacturing. Companies are using the flexibility of additive to create fixtures and assembly aids to get their products from the computer to the shelves faster. And with the emergence of faster additive technologies like DLP, high-speed sintering, and bound metal binder jetting technologies, the feasibility of production AM parts is no longer limited to just aerospace and high-end rail applications. Markets including consumer goods, automotive, and even sportswear are beginning to make use of additive manufacturing. But here's the kicker. Additive manufacturing has some pitfalls for use in production applications that you need to be aware of. Because at the end of the day, the NFL Challenge Committee is not going to take some half-baked solution. And they are going to expect that the challenge participants think through the risks of advanced technology choices. So let's actually go to the official rules here. And we're scrolling through some really important things. Don't miss those. But the most important thing here is the judging criteria, right? Okay, so number one in the assessment criteria, the helmet performance score. That makes sense, right? What's the HPS score? Just under that is this very vague statement. Is the submission feasible for use in the NFL? Very vague, and it's the only time the word is used in the entire rules. So I'm going to help you think through what this requirement is that is second only to the actual helmet performance. First of all, is your design repeatable and repeatably functional? Is it adoptable? The bullet under the feasibility bullet back in the rules talked about this too. Will teams actually take the helmets? Are they on brand standard with the NFL and team logos? Are there any environmental grenades packed into the design, etc.? Third, does it pass the throw it against the wall test? So this rule comes from a general rule that some of the engineers at Blueprint use for minimum durability design. Don't design something for the way it's supposed to be used. Design it like the person you just handed to is going to chuck it against the wall. Because especially in the world of manufacturing, and honestly sports for that matter, it probably will have it. So is it durable off the field, not just on the field? During transport, what about storage? Is it good in moisture, in heat? You get the picture. Is it serviceable? Will your design be a nightmare to clean, repair, etc.? And finally, perhaps in summary, is the solution scalable? Will there be any roadblocks making 10 of these things? What about 100? What about 1,000? What about 1,000 in different colors? The NFL is investing real money into this design. And so what if they want to license this technology to other equipment providers or users? So scalability is an important part of feasibility for this contest and in good engineering design in general. But as I've said, additive has pitfalls that you need to clear. Don't let additive get between your final solution and that important judging criteria. Okay, so what are these pitfalls in AM scalability? So Blueprint has seen production additive applications fail dozens of times, maybe hundreds at this point. And generally speaking, there are three categories of failures that cause a production application not to succeed: value, data, and change. So let's look at value first. And specifically how underthinking part value can cause an additive manufacturing application to be at least a perceived failure. And when I say value, I'm literally talking about the economics of the part. It doesn't matter if the NFL helmet challenge is a design and physics challenge at its core, the cost of building the helmet will play an enormous role in the, quote, feasibility of the submission for the NFL. So to show you the particular challenge that part economics plays with AM, we're going to compare two aftermarket automotive parts. One additive, the other traditional. So the main cost contributors to any manufacturing part are tooling, logistics, processing, or manufacturing, and the actual cost of the material that goes into the part. And although the actual cost buckets don't really change between additive and traditional, what goes into each bucket does change and how much money. So for example, for the additive part, tooling and logistics don't really contribute much cost at all since it utilizes digital tooling and there's really no need to keep inventory on hand. But the process and materials are going to be expensive because AM is a fairly complex process compared to most traditional manufacturing. And the equipment and materials tend to get pretty pricey. On the other hand, with traditional manufacturing, the tooling and logistics costs end up being more expensive components due to batch manufacturing. And the processing is usually short and automated. The materials are often commodity, bought in bulk, so they're pretty inexpensive. So why does this matter for scalability and part cost? Well, tooling and logistics are the biggest contributors for low volume production since they're fixed costs. And process and materials are the biggest contributors for high volume production because they're variable costs. So you can see what I'm about to get to here. And that's how you get this famous genre of graphs talking about traditional and additive manufacturing. If you haven't seen one of these before, I highly recommend a website called google.com. Go look it up, traditional versus additive costs. Very common things among all of these, which basically shows the convergence of traditional and additive costs at some point over a volume. And the point here is that traditional manufacturing is more cost effective for volumes under this convergence point, and that additive manufacturing is more cost effective for volumes over that point. But I will say this isn't the whole story, and this is what I'm saying about the value being underperceived and under-recognized is the real pitfall here. There's one graph here telling a different story. This graph isn't measuring the cost of a part based on volume, but actually its complexity. And the story here is the opposite. The cost of a part increases with complexity for traditional until some point at which additive is cheaper. Okay, so there are more dimensions than just this typical volume dimension that we see on the x-axis in lots of these graphs. There's actually lots missing from these graphs, and it's not just volume and complexity. There's lots of dimensions here. So a simple two-dimensional graph isn't going to be enough to make an educated financial decisions on whether to use additive or traditional manufacturing. So for example, what about the risk of part obsolescence? That needs to be factored into the decision. Or the cost of uncaptured market due to stockouts. What about the flexibility and reactivity of additive manufacturing? How about penalties or costs of causing lines down or idle equipment, especially in regulated industries and industries where suppliers commit to a certain level of service? These can be really significant. And I'm not going to go through all of these, but the list goes on and on. These considerations that involve additive versus traditional all need to be considered before making a good justification for choosing one or the other. Because what happens if the business case isn't thought of holistically? Production additive manufacturing programs can get shut down early or never even take off because their full business value hasn't been considered. They become a low volume solution. So that's why Blueprint created the 6 business drivers framework. Over the last 16 years of observing and advising the additive manufacturing industry, Blueprint has collected the core 6 business drivers for using additive manufacturing in business. And you'll notice that the only one of them is called low volume manufacturing, that 5th one. The other 5 explore other physical business value to be delivered with additive manufacturing. So within each of these business drivers is a set of tactics below it that companies all over the world are using today. Each tactic is something quantifiably valuable about additive manufacturing, something to support the business case for using it. There are 50 tactics in total. So we call this our 6 business drivers and 50 tactics framework. I've hidden some of the drivers that probably aren't useful for the NFL Helmet Challenge on this slide. But the rest of these should all honestly be considered as a reason for using additive manufacturing for the helmet design, and use them when creating a business case or business justification for additive as a solution. So to give an example of how to use this framework, I'll use an example from another industry, but you'll see that the drivers apply to all kinds of industries. Most people familiar with additive manufacturing know the story of the GE LEAP engine fuel nozzle, which used additive manufacturing to consolidate a bunch of virtually unmanufacturable, uncastable parts into just a handful. And a close and possibly more impressive cousin of this story is the Cessna engine project, which used 3D printing to redesign the engine assembly design from 855 traditionally manufactured parts into just 12 3D printed ones, which is almost a 98% part count reduction. So without a doubt, one of the biggest business drivers being used here is the freedom of design, and specifically tactic number 1 with that business driver, or assembly consolidation. Without the business drivers framework, the other value provided by AM might go unnoticed, and this might be our entire business case right here. But that's not the case. There's other things to consider. So, for example, in staying within the business driver of freedom of design, there are other tactics at play here. Lightweighting, which would reduce the weight by 5%. And so we're making use of other tactics like biomimetic structures, because this one of the housings on this vehicle was, on the engine, had its weight reduced by a significant amount by using a biomimetic structure that reduced the weight of the aluminum component. But there's more value though, and this time it's coming from other business drivers. Streamlined supply chains. 35% of the engine was produced in-house, reducing the assembly time and cost of logistics for this part. So also an increase in design change responsiveness reduced the costs to customize the engine for particular airframers that had specific requirements for this engine, an often hidden fixed cost in acquiring new business. So in the case of the NFL helmet, this tactic might be used to overcome any startup costs associated with customizing the helmet for a particular team, or a field position, or a specific league requirement. And finally, especially because this is an aerospace application, there are a host of environmental benefits to using additive manufacturing. For instance, there was 20% less fuel burn, which is an environmental benefit. It had a 10% power increase with the help of design for function geometries, and ultimately, at the end of the day, lower maintenance costs due to the assembly consolidation. It can be more intentionally designed for repair. So with a new mindset, we can see that the GE turboprop case study and the Cessna case study are far more advanced than they might appear. They're really quite robust reasons for using additive manufacturing, just beyond the specific cost reduction and assembly consolidation. So by using the 6 drivers framework, we can clearly see that the success of this business case is not pinned to one single benefit, that if there was a hiccup with that, there are other reasons to fall back on additive as a viable solution. It's really important to have this holistic view of additive, especially during a time when people are still trying to figure out what it's used best for. And so it's important to have a bird's eye view of the overall value. So here's the rub. 3D printing provides a range of new possibilities for business, from part design to supply chain configuration, but many of these opportunities are still hard to quantify and difficult to project a firm ROI. So to improve your chances of success, it pays to create a proposition that leverages as many business benefits of additive manufacturing as possible. The hard work of quantifying these benefits remains, but even just the fact of diversifying an additive value proposition is useful in justifying the use of an expensive technology. Okay, so that's the potential pitfall with value. Sometimes it's tough to quantify, but to make a full business case, all the ways that additive assists a solution need to be considered. So this next hurdle we're going to talk about to clear is that of data. And to explain this, I want to first explain what is so different between traditional and digital tooling. In fact, there's a deep chasm between traditional tooling and digital tooling. It's the difference between a hand-polished 200-pound steel thermoforming tool or injection molding tool and a thumb drive with a 3D printing file on it. One of them is virtually unchanging and permanent. The other is flexible. It's easily moved, deleted, or improved. Traditional tooling is used to make one single thing over and over. It doesn't need production flexibility, movability, or the ability to iterate a design. On the other hand, digital tooling is flexible, customizable, and exhibits virtually no tooling change fees, just the cost of updating a file in a database. It's used to making lots of different parts on the same machine with the same equipment in different batch sizes. With the repeatability of traditional manufacturing naturally comes some reliability and high precision. With the rigid tooling comes rigid processes and therefore rigid outcomes. Traditional tooling may require hand polishing, a little knob turning, or other adjustments to get what's needed, but once that process is down, it's really precise. Digital tooling is naturally more complex, which generally reduces the accuracy and precision of the part. For example, take injection molding. A moderate complexity injection mold takes months to design, manufacture, hand polish, and test, and rework and hand polish and test again. But once it's running, it makes exactly the same part it was supposed to create. Every defect is rubbed away over the long weeks of hand polishing and fitting. Digital tooling is almost entirely created using automated softwares that turn CAD into parts. But that doesn't change the fact that AM processes are still very complex and delicate ones compared to traditional processes. So what if additive is, so who cares really, right, if additive is complex? Well, managing a complex process in a scalable manufacturing environment comes with its issues. And when it comes to the NFL football helmet challenge, odds are good that you'll be making use of the embedded functionality business driver, an indication that your parts are going to be complex. So take, for example, a lattice structure, probably front of mind for the NFL helmet challenge. A lattice can be thought of kind of as a happy medium between nothing and everything. In terms of weight, it's right between a void and a solid geometry. And that goes about the same for strength, although the different direction. But let's say we want to make use of this shock absorption business driver tactic under the embedded functionality business driver, right? So let's go back and see how that is affected by a lattice. And a lattice is really the best option when it comes to shock absorption because of just the nature of the geometry and the performance of the materials. But it's also the most complex by a long shot, geometrically complex. In fact, the best additive designs, the ones using the most business drivers, the lightest ones, the fastest ones, the cheapest ones, they all tend to be fairly complex designs. Okay, so let's get more specific about what's so difficult about these complex data-driven designs that only additive manufacturing enables. Well, the entire process of using data-driven designs has pitfalls, from collecting the data, the input data, to designing with that data, and finally manufacturing the designs made with that data. So first, collecting input data. The first pitfall is not having sufficient infrastructure to collect personalized data. Okay, so this is kind of specific to when you are customizing a geometry based on custom requirements or personalized requirements. And so let's take, for example, the Adidas Futurecraft shoe that is probably fairly familiar to lots of viewers. Did they commercialize a 3D printed running shoe midsole? Yes. Did they deliver on their intent to create personalized shoes? No, at least not yet. Okay, why? Well, there are lots of reasons. And it's extremely difficult to turn a commodity shoe market into a custom shoe market, for one thing. Do customers want to spend hours getting fitted and taking measurements? How will their foot data be collected? Are they willing to wait for a custom shoe to be made? There's a lot to consider here on the front end. So that's kind of how this pitfall manifests itself. There's not enough infrastructure or market analysis to make sure that a custom data-driven design is actually the right solution. So the way to jump over this pitfall is to perform an analysis of the user experience to make sure that data capture actually fits the product you're trying to, the need that you're trying to solve. The second pitfall is that of natural variation between designs and the impact of that variation on part performance. This is especially true of regulated industries where parts need to be certified or have some minimum level of performance to be acceptable. So with respect to the NFL helmet challenge, for instance, does customizing this solution to fit a particular head size, shape, or other player-specific trait have an effect on the effectiveness of that helmet? What happens if you change the size or the shape? Does it still do what it's supposed to do? The way over this hurdle is to research and communicate the impact of particular part design customization of the performance. If changing the design affects a critical performance variable, you obviously can't do that. So you try to isolate those variables and test the limits to make sure that customization isn't undermining the value of your part. Okay, so those are the problems with collecting the input data. So the next problem is designing with that data. The first pitfall to be aware of is probably a pretty obvious one, but it should still be said, which is that it's tough to turn data into geometry. Again, the NFL and any technology adopter is looking for a solution, not a technology. Big misconception in this industry in general. We have to be providing solutions in general, not just particular segments in a technology chain. Just because the collection and complex designs are both more advanced than ever doesn't mean it's easy to connect the two. The way over this pitfall is to create algorithms that generate families of solutions instead of one-off programs that need lots of manual tweaking and mesh editing with little vertices. So software companies like N-Topology use a programming approach to create part designs so that lattices, texturing, and lightweighting can be performed on many different base geometries, and then applying a common code to them to create families of parts without having to retool the whole process. The second pitfall for designing with data is that there is an undeveloped business case for a complex design. It's rarely true that design complexity is in itself more economical than a simple design. So that's why we have recourse to the business drivers to justify why added complexity is being added to a part. Okay, so that was designing with data, but there's actually also some complexity with manufacturing these data-driven designs that you should know about as well. So first of all, complex designs are just inherently riskier than simple designs. As we discussed when I explained the idea of digital tooling, the simplicity of melting plastic rushing into a metal injection mold is being replaced by a much more complex process, with thin layers of polymer or metal being stitched together into what could kind of be thought of as a big 3D quilt. It's full of forces, excess material, and always a degree of error. The more complex this 3D quilt needs to be, the more chances for a loose stitch that could cause non-compliant results, or even total build failure and machine damage. So to avoid this, to jump over this pitfall, educate yourself and your stakeholders on the limits of the technology and try to stay within the green zones of complexity for that particular platform, material, and operating condition. And I'll be honest, this can really just be acquired with practice. Lots of practice, lots of expertise. So second, in order to introduce personalization or customization, the process requires individual setups, fixturing, or post-processing procedures. If this is true, this is going to cause a problem in scalability, because what happens here is that the process can't be streamlined. If we refer back to the Adidas shoe, think about that future state in which they're running all sorts of different geometries at once on one manufacturing line. Each individual midsole is going to require a different amount of time to build, have supports removed, be cleaned, post-cure, and also stored. Design complexity has suddenly just become process complexity. And process complexity means hand-holding and makes it very difficult to automate. The advice on this pitfall is similar to that for managing complex designs. Keep design variation within that green zone of a single process as often as possible to maximize the potential to streamline an operation as you scale, as you increase the variations on a particular part, or as you increase the volume of those parts. Okay, so we just talked about 6 unique pitfalls within the data problem of additive scalability. And that got pretty technical. So hopefully I can give your brain a breather with this last consideration, change and change management associated with additive manufacturing. I'm going to start out with a couple of statistics from a recent Blueprint survey. Of the 200 business leaders responsible for AM in their organizations that we spoke to on this survey, 84% of them were trying to move their additive adoption out of prototyping into fixturing, production, etc. If we harken back to that sphere of additive capability we showed earlier, trying to expand the sphere within their company. But 85% of them also said they're stuck because of technical and business knowledge. And when we started prying deeper into what this knowledge barrier really was, we found 3 disconnects happening within an organization. First, there's a disconnect between the why and the how of additive manufacturing. The various engineers, designers, and business leaders all wanted the results they were promised with additive manufacturing, but they had completely different ideas of where that value of additive really was. Second, we found a disconnect from reality. Understandably, there is confusion inside of organizations about what additive really is, how the technology works, what equipment's involved, what can really be produced today, what can't. It's changing every day. So this disconnect is really understandable. And third, there's a disconnect from real design tactics. So remember the 6 business drivers framework? These are only useful if designers actually know how to make a difference using them. For example, designing parts to use less material looks really, really different depending on what technology and even material that you're building with. So we started showing our customers how to overcome these disconnects, these knowledge barriers. We call the mindset that we teach thinking additively. Learning to think additively helps organizations avoid gridlock. The various departments of organizations aren't able to adapt to the change involved in making something additively. Sourcing, supply chain, engineering, manufacturing, sales, service, product management, these all have to be on board, speaking the same language, understanding the same constraints, leveraging the same benefits in order to make additive products a success. And don't be fooled, NFL will be the same way. Again, I'm going to go back to what I said earlier. They are looking for a solution, not a technology. We have to be able to provide a solution to them. And a solution involves something that will work for their organization. At the end of the day, it's eliminating these disconnects that's going to continue to grow the sphere of additive capability in companies and the industry at large. Okay, so how do we leap over this pitfall? Make sure the organizations you recommend to use additive are thinking additively. So my time with you is almost up. And learning to think additively is a journey more than the 2 or 3 minutes I have left here. So I'll just give you 2 ways you can continue to upskill yourself on thinking additively and recommend to anybody to whom you're providing AM as a solution. First and easiest, go get the Blueprint Business Drivers book. It's called The Little Blue Book of 3D Printing, and you can go download it for free at additiveblueprint.com. Easy. You'll see each of the 50 business drivers tactics in action and how real companies use 3D printing to create value right now. If you're looking for more on our Think Additively mindset, later in April 2020, we're actually going to be doing a first ever digital workshop on using on what is our usually in-person Think Additively training. If you're interested in learning the best of DFAM practices from myself and a couple of my colleagues, there should still be some slots available for this 5-hour workshop spread out across the week of April 13th. So if you're watching this sometime after April 2020, the link will redirect you to other ways you can engage with our Think Additively workshop. So those were the 3 problems with additive scalability. Remember, additive manufacturing has countless ways to add value to a challenging project. It is important, though, to make sure that the final recommended solution is feasible for the final customer. In the case of the NFL Helmet Challenge, they found it so important, they put it straight in the rules. So that's all for me. I hope this was useful, and if you had any thoughts, please reach out to me at david@additiveblueprint.com. And in case I'm away, why don't you copy hello@additiveblueprint.com so that somebody from our team can get you an answer right away. It's been an honor to spend time with you to discuss scalability of additive manufacturing. On behalf of the whole Blueprint team, cheers and stay well.